Hello, good afternoon, everyone. So, my name is Abhishek Munshi. I am a PMRF research scholar at IIT Jodhpur, and today is our last lecture regarding the design of power electronics. And today, our agenda is to see the different sections of a power converter. Taking a particular power converter, we will see its different sections and what are the parts a power converter has. We already discussed all the different aspects of designing a power converter, and today we will see it in a converter, that how it will works and how it will look like, how the converter behaves, and finally we will discuss about designing how to design a PCB in a brief. Okay, so the different sections of a power converter regarding, first we have to discuss about the power electronics in it, and obviously the switch. If you are using a MOSFET, IGBT, then it has a dedicated gate driver. You have to use it that way. It's into the gate driver. We discussed a little bit more on the gate driver class, that it has a level shift circuit, it has a microcontroller unit and all. Okay. So next part is the controller unit. You definitely need a controller to generate the PWM to switch on and switch off the converter switches. Okay. And in power converter, we should have a sensing circuit, so uh, which can sense out the current and the voltage, and based on which it can mm, fed it back into the controller to control it in a controlled manner. Okay. So obviously a control power converter is used. Okay. Next, there are some interfacing circuit, because while after sensing the circuit, we should have to send it in the microcontroller to control it. So definitely we need ADC interfacing circuits, and sometimes we need level shift circuit and all. So that is an interfacing circuits. And power supply. Suppose this is a figure of a three-phase motor drive by Wolfspeed for 7.5 kilowatt. And in three-phase motor drive definitely means a three-phase power inverter is there. And for three-phase inverter, suppose you have to give a uh, power supply. uh, so power supply, definitely we use a DC converter into it for SMPS purpose, for switch mode power converter. So basically in most cases we use a flyway converter. Next, in cooling and enclosure, as we discussed previously, that in case of the converter design, and the converters, whenever you sell it in outside, there will be an enclosure in it that is called a chassis, and it definitely needs some kind of cooling systems. So it should have some fan for cooling. It have some proper heat sinks, thermal paste. So make it proper way functioning. So we will discuss step by step into it. Okay. So this is the final uh, class. Uh, Wait a minute. So these are the different parts of the power converter. So if you have any doubt up to it, you can ask. Okay. To this, if you have any doubt, you can ask. Okay. And we will move step by step into the converter design. Fine. So step one, which is the power electronics into it, we see that the converter which I showed over there, it has some EMI filter protections. We discussed this in the last class that a converter definitely needs EMI filter protections. And after which you're supplying a AC, so there will be a three-phase rectifier which will convert it into DC. And this is a rectifier, and this is the DC bus capacitors. The DC bus capacitors, okay. And after which we have the three-phase inverter, which will convert from DC to AC, right? So that AC is used for the motor drive purpose. And here we have power controller power supply, that is a power supply we dedicatedly use for car controller and gate driver circuits. And yes, okay. So this is the basic power electronic into it. This is a motor which is used for in this purpose for driving. Uh, this is the three-phase inverter. So we were to discuss about the DC bus capacitors, why we use that to maintain a constant DC voltage across it, and these are the resistances which are used for mm, sensing the DC voltage. Here we'll discuss it in a previous in few more after lectures. Slide. So this is basically the power electronics in the power converter. Definitely a power converter can't be possible without power electronics into it. We already had discussed many things in the first and second lecture about power converters, the DC-DC power converters, buck converter. We discussed about boost converter, buck boost converter. We solved how to design it, and we discussed about edge bridge. Okay, so this is a part of that, a power converter. You definitely need power electronics. Without power electronics, you can't develop power converter. Is a part of power electronics. Okay. So next, whenever you're designing a power converter, definitely you need a gate driver, right? So what happened gates of the gate driver? We discuss about gate driver in a separate lecture. Then what is the role of a gate driver? Is used for driving the gate pulse, because uh, to switch on a MOSFET and IGBT you require a certain voltage level that is above the PWM switch voltage level. When from a microcontroller, whenever you're giving a PWM, when we generate a PWM like this from a microcontroller, it has a maximum voltage level of 3.3 volt or 5 volt. So if you're using a Texas board, a Texas dedicated microcontroller, it should have 3.3 volt. If you're using an Arduino based microcontroller, it will have 5 volt and all. So different microcontrollers have different HDR voltage. Okay, so but this 3.3 volt or 5 volt is not enough for driving your MOSFET or IGBT which you are using. So it definitely requires more than 10 to 20 volt for driving that. So in that case, we have to use a gate driver circuit to pull up that. So the gate driver circuit has a level shift. So it used for level shift that voltage of the PWM to drive the MOSFET or the IGBT. So, and as we discussed previously about many gate drivers, that a low side gate driver, a high side gate driver, and bootstrap type of gate driver, which it has both the high side and low side. So, okay, and also we discussed about optocoupler based gate driver. So, here in this kind of in this specific inverter which I am showing, it has as based on the lecture of this week, it has a high side gate driver, it has a low side gate driver. uh, this is using a specific IC for gate driving. So this is a Texas controller board where from you getting the PWM pulse and then you sending it into the gate driver to ultimately driving the MOSFETs here. So one is dedicated for the high side MOSFETs and IGBTs. One is dedicated for the low side MOSFET and IGBT. So that is this is the low side driver. This is the high side driver. Okay. So next is that the power converters. For controlling the power converter, we require a dedicated controller. So in this power converter, which I was shown on the first slide, if you see the first slide, that this is the controller which is here. So this controller is basically a TMDS CNCD 20039C digital controller of Texas, and there are many other Texas microcontroller board. This is very popular. This is Launch Excel F283798. This is Delfino. This is under the Delfino. So this is one of the most popular wide used microcontroller, which is not used in this case, but this is one of the most popular used microcontroller from Texas Instruments. And this is one of the docking station type microcontroller from Texas Instruments. This is TMDS PRX288335. There are many others, F28335. This is from Delfino. There are some Piccolo launch pads. So based on various Texas, they have provides various microcontrollers which you can use for your power converter design. Apart from the Texas board, you can also use some Arduino boards like Nano, Uno, and for powerful purpose you can use Do, Mega. Other than that, there are some STM Cortex Phantom microcontrollers are there, so you can use that also. So, but the most preferred microcontroller in case of three-phase design and high power design is uh, this kind of Texas Instrument microcontroller board, and this is the most popular board, F28379D. But in this case, we are using has they use Toolspade has used this one, this digital controller. Okay, so this digital controller, if you see it in all the cases, in all the board, there is a chip. This is the main microcontroller chip, and the race circuit as a driving circuit of this microcontroller. Okay, so it has some communication panels. It has some protocols like SPI can that supported this. It has some ADC, it has some DAC, so all are included in this controller board. Okay. The next part is designing a power converter. You require the sensing circuits. Okay. So obviously, if you are going to control the output voltage or the output current of a power converter, you should have to sense the um, circuits, voltage, and current. So for current sensing purpose, you has some dedicated current sense amplifier. So this amplifier is used here, AMC130 MD520 BWR. So this is a plus minus 50 volt input precision current sensing amplifier. So it has a 20 megahertz clock. So this is for current sensing purpose. So obviously this is like a amplifier. Suppose this has a plus minus. So if you have using a sense register, suppose R sense, and here you put V1, suppose here V2. If you give here V1 and V2, you will definitely get a sensed voltage based on this current with a multiplication of gain based on the IC you choose. Okay, so, fine. So suppose here 5 amp current is going and you use a 0.001 ohm sense resistor. So obviously you will going to get a zero point 0.5 volt. Sorry, 0.005. So suppose it has a 100 volt per volt gain, so you will get a zero point 0.5 volt output at this. So after which should have to use some kind of interfacing circuits for proper maintaining its gain and all. So these are the function of current conditioning circuit. Another one is a DC voltage conditioning circuit. So this is very fundamental. So if you add a slide, how could you get the DC voltage? Suppose you have a DC voltage here, suppose VDC you're giving, and nothing you should have to do. You just use a potential divider across it and set the gain accordingly at how much voltage the ADC of your microcontroller unit supports, based on which you scale it and get the sense voltage and send it into a suppose a op amp. You can send it into op amp for a buffer circuit. So, okay, so you can send it here for a buffer circuit. So this one is plus and minus. This is a inverting buffer circuit. So after which we'll finally get the sensed voltage. Okay. Here in this case, if they use a dedicated IC, the current sense amplifying IC, they are sensing the voltage and send it into the ADC of the microcontroller. Okay. Next is voltage conditioning circuit. Obviously, as I said, that after getting the voltage from the sense circuit, you should have to send it into some kind of op amp for maintaining the gain and for refining it and then send into the ADC. So obviously, if you have a high voltage, you should have to maintain it properly. You have to design a proper system so that you can able to send it into the ADC of the microcontroller, because as I said, the microcontroller can support more than 3.3 volt. In some cases, some microcontroller supports up to 5 volt. So if you're sending a 21 volt after sending it into the microcontroller, then it will damage your microcontroller. It will not allow negative voltage also. Okay. So you should need a interfacing circuit. So this is the kind of interfacing circuit they're using. So in this dedicated inverter circuit, so they're using a lot of resistor because to for the potential divider. So they're not using a single resistor, but using a suppose multiple resistor to make it good design. This is so more and more resistor will make the circuit uh, protections better. Okay. So up to this, if you have any doubt that we discussed about the in a power converter, we have the basics of we require microcontroller unit, we require gate driver, we require sensing circuit and interfacing circuit. So if you have any doubt regarding of this, you can ask me. After which we will move into the next parts of the power converters. Okay. So while designing a power converter, you should have to keep it in your mind that you should design all these things that all the classes we covered. So that's why I'm summarizing this, that within a converter design, that what the role of those things which we discussed previously, the gate driver, the EMI circuits, what's the role of that? So basically they are used in a power converter, how they looks like in a power converter. So that's why we are showing these sections of power converter, the parts which are used, and we'll discuss some components, equipments, and then we'll discuss about how to design the converter at last after the circuit diagram and all. How could you design it by means of printed circuit board? Okay. So after this, if you have any doubt, you can ask. If you have to note something, you can note it down, and then we will discuss about the next part. Fine. So the next part is includes the power supply design. So we already had discussed in some previous lectures that how to design power supply, switch mode power supplies. So they're basically DC-DC converters. They are categorized. We discussed about non-isolated, isolated. Into non-isolated, we discussed buck converter, buck boost converter. In isolated, we are using flyback converter. So in this specific inverter design, they are using a power supply of plus 12 volt flyback converter. So this is the design of that flyback converter. So this is the switch of the flyback converter. So this is the coil primary and secondary side. Basically rectified it, and you're getting a plus 12 volt dedicated output power supply. That power supply is used for the supply of the gate driver. That is used for the power supply of the sensing circuits. Also, if the op amp has a high voltage rating of VCC of 12 volt, if it is 5 volt, then they're taking it from the controller unit part, and This is the power supply which is used for the gate driver and other parts of the circuit which requires the power supplies. Okay. Next part in converter design is the cooling and enclosure. So if you see that if you have a MOSFET, we discussed it previously in heatsink design, that in the MOSFET we use some kind of heatsink, right? Whether it is SMD, whether it is through hole, we use some kind of um, heatsink. I also had discussed a way of SMD heatsink, that in case of SMD, we put some vias behind the MOSFET where you're placing the MOSFET for bypassing the heat from the copper plate. So that is a way in case of PCB design for SMD, we can use multiple vias around it, so to avoid the heat generation. And this is in a device level, in a converter, in a device level, you're using a heatsink for protecting the um, thermal management, for heat temperature management you're using. But uh, in an wider way, whenever the whole converter we are thinking about, we should have to use a dedicated heatsink. Suppose in some converter they use a whole block of heatsink behind of this or upper of this, and they use some kind of cooling fans. These are some DC cooling fan for supplying. This also we require 12 plus 12 volt, which can we get from that flyback power supply. So these fans also require 12 plus 12 volts. So these are cooling fans. This can also use for cooling for the overall system of the converter. And we have discussed about the enclosure. So whenever you're selling a converter, it should have an enclosure into it, because uh, the converter should not be in bare way. So that you can, suppose the inductor is heating, inductor is charged, and you can touch it, so it will uh, damage yourself, right? So a basic protection required. So that's why, yeah, enclosure is always there. So this is a chassis we use. Okay. So these are the basic parts of a power converter. And next, we will discuss a little bit about capacitors. So, how to choose capacitor? What are the different types of capacitors? So, this is the parts of the converter. So, regarding this, if you have any doubt, you can ask. Fine. So, next part where we move into it, this is the selection of capacitors. So, while designing a power converter, you require capacitors, resistors, inductors. So, inductor design we had discussed previously. So, what are the basic features we require for designing inductors? We discussed it, the core, the wire, how much current is flowing. So, that is the main thing while choosing an inductor. If you have to think about the current, the how much resistance it has, the equivalent resistance. So, you should have to take in that part into the account. But we didn't discuss about capacitors. So, they are basically three types of capacitor. One is electrolytic, film, and ceramic. More are capacitor types are there. The tantalum capacitors are there. They are basically sold with electrolyte. So, so if you see this graph, this is the power range up to which the capacitors covers. The ceramic capacitors can be used for high voltage also. So while choosing a capacitor, you should have to keep in mind first the parameter we should choose, that is the voltage of that capacitor. After which you have to see the ESR of that capacitor, how much ESR it has. ESL is generally is not given in the data sheet, so you should consider that. But two main things you should have to consider while choosing a capacitor is the how much ESR it has and how much voltage level it has. Suppose you require a you're designing a converter for input voltage range of suppose 100 volt, and you choose a DC bus capacitor of 25 volts, so it will not work, right? It will burst, it will damage your circuit, right? So you should have to keep in your mind while choosing the capacitor, voltage is very important. Another thing is that ESR. So what is the effect of the ESR in the circuit? Suppose you have a high ESR based capacitor, you choose having a suppose 1 ohm resistance. So that resistance will make a voltage drop, a definite potential drop across that capacitor, and that will affect your circuit in further. Suppose you require a 24 volt supply and you're getting a 22 volt, that there may be a huge loss across it, right? So you should have to keep in mind that voltage and ESR are the two major factors. So if you see here, this is the aluminum capacitor, these are SMD. These are not actually SMD, these are SMT. So this can be used both as a through hole component and as a SMD component. So you can see that this is the cap over here. If you remove it, you can use it as a through hole, and if it is there, you can use it as a SMD, the surface mount device. So these are aluminum capacitor, poly aluminum poly cap. Okay. And these are electrolytic capacitor. These are also along aluminum. These are some electrolytic capacitor through hole. So basically we use electrolytic type of capacitor for DC bus purposes, for filtering. So these are some SMD capacitor. So sorry. So these are some SMD capacitors. These are tantalum capacitors. So these are having electrolyte. So these are the thin film capacitors. So if you are using high frequency, so mostly in case of high frequency, these thin film capacitors are preferable. And these are the ceramic capacitor. Ceramic cap. This is SMD version of it, and this is the through hole version of it, THT. Okay. So ceramic capacitors are mostly preferred in most of the cases. Most of the part of the converter, whenever you require a capacitor, we put without going into deep of it, we put ceramic capacitor, just checking its voltage, and yes, it is generally low, so you can choose that. For DC bus capacitors, for filter capacitor, we generally choose this kind of capacitor, the aluminum capacitors. And for high frequency purpose, in case of wireless and all, we use thin film type of capacitor, because electrolytic capacitor doesn't work over there. It can burst and damage your circuit. It can cause fire. Okay. So if you see here, this is, we already had discussed it in the EMI class, that we have if the equivalent circuit we consider in the capacitor, it consists of ESR and ESL, equivalent series inductance and equivalent series resistance. So you should have to consider the resonant frequency. So this is the calculation for the resonant frequency, and you should have to check this curve, that how much frequency, at how much frequency, how much capacitor we are getting, and based on which how much will be the effect of the ESL. Okay. So you have seen that this is for the aluminum elco. This is for aluminum elco. This is for MLCC, that is multi-layer ceramic. Okay, so it has sub. Why we use basically use MLCC? This is for high voltage. Many ceramic are used at a strand, or in some cases inside of it they are using that. So that kind of capacitor are called MLCC, multi-layer ceramic. Okay, so by another factor, if for choosing capacitor, if you see from the phasor that this is the resistor ESR part, this is the capacitor, and the inductor will obviously be lagging over here. So you should have to consider the dissipation factor. So if this is delta with the angle here, so that tan delta, if you can calculate it by RS omega CR. So CR is your capacitor and RS is your series resistance attached to it, and omega is the frequency, okay, at which you're operating that capacitor. So you can get the dissipating factor uh, of the capacitor on that case. Other capacitor specification which you can keep in your mind, that is RMS current rating, the DVDT rating, a failure rate of that capacitor. But most important part, we can say, on voltage, you have to keep in your mind obviously the ESR. These two are the most important things, and the rest you have to consider for good design. Okay, so okay, fine. So this is about the capacitor. So if you have any doubt of this, you can ask me, and we'll move forward. So next is the type of the component. So you should have to familiar with the component while choosing. So basically, there are two types of components we use. One is through hole. In short, we can write it as CST. Another one is surface mount device, or SMD. So this is a surface mount register, and this is a through hole register. So in case of surface mount, there are some different packages based on their sizes. Suppose different 2220 package, 1805, I think 0605. There are some two packages, 1210, 1206, 0805, 0603, 0402, I think. So these are the different packages. So this is a little bit big, and this is lesser bigger than that. And now I'm coming to this. You can see that this is more and more small. So For surface mount device, if you use surface mount device in a converter design, it will take less space. And what will be the advantage of it? If it takes less space, the PCB we are designing for the power converter will be smaller and compact. But in case of through hole, if you use, it will require more space, right? You can use that through hole component. This is a vertical way. You can also put it in that way, the register, right? So fine, horizontal, vertical, two types of way you can place it. So this is the advantage of surface mount. But the another disadvantage is that for surface mount device for soldering, you require a dedicated soldering station for it. You require a heat gun type. You require actually reflow oven. Actually, you require a reflow oven. So this is a specific kind of soldering station we require for surface mount device, which is not required in case of THD, as soldering rod will be enough for THD soldering, right? There is some advantage, obviously comes with some disadvantages, some criticalities. Okay. If you have any doubt, you can ask or note it down and we'll start. Sorry, there is a network issue, so that's why it got delayed. Okay. So, so this is the next part where we are discussing about the registers. So these are the through hole type of registers, and discuss shown that this is the assembly type of register. Next thing, uh, which we require about to have to familiarity while designing the power converter is the measuring equipment. So one of the most important measuring equipment which we require is the oscilloscope. Is the oscilloscope, right? So oscilloscope has some dedicated parts which you have to understand that it is used for measuring the current and voltage waveforms. So this is for the channels where you can see the waveforms. These are two channel waveform. So we require probes for measuring it. So one of the this one is a differential probe where we use for measuring differential voltage. So this is a differential probe. This is a passive probe which can be used for. Sorry, I'm facing an internet issue, so some wait for some time. So. So I was discussing about the probes. So this is a normal passive probe which you can use for low side measurement. Differential probe which you use generally for high side measurement, and this is a current probe which you use for current measurement. Okay. And while selecting the probe and the scope, you can see that the probe has a dedicated frequency. The oscilloscope has a dedicated frequency. So how to check the system bandwidth calculation? So this is the basic formula for calculating the system bandwidth, that how much bandwidth it will offer. So that is 1 by root over of the 1 by scope bandwidth square plus 1 by probe bandwidth square. So if you have a 100 megahertz scope and a 100 megahertz probe, you will get only 70.7 megahertz of system bandwidth, not 100 megahertz bandwidth. Okay. So bandwidth is essential while for high frequency applications for measuring. Okay. So it can capture more noises, the harmonics, but in case of high frequency, uh, if you are using a suppose a low bandwidth device, then it will not capture the noises properly. So next and the important step is designing the power converter in a PCB. So PCB can be designed in open software, one that is KiCad, you can freely download it, or there are EasyCAD or EasyDA, you can say that. And there are some professional softwares. One is Eagle, Altium. So that requires a definite license for designing PCB. So while designing the PCB, first step you have to design the circuit. You have to design the schematic of the power converter which you want to design. And while designing the schematic, you have to choose properly the values and the packages. You have to choose properly the packages, proper footprint of the component which you are using. Otherwise, it will show error. So after that, you have to check the ERC, the electrical rule check, that if your circuit have any error, that if any connection has been lost, any connection has been not connected. So you have to check ERC, after which you will go to the PCB design. So in PCB design, if you have any error in your schematic, that will not followed, and that design rule check will not give anything wrong, but you have a mistake inside, right? So properly you have to choose packages and footprint. So component footprint, if you see that there are different component footprint, these are the component footprint for some ICs, microcontroller ICs. Basically follows these footprints, QFP32, there are TFP, this is for the trim port. Okay, so this is DIP pin. So these are for the diodes, transistors. So these are different footprint. You have to properly choose the footprint, the second step while designing the PCB. Next, the most important thing is the placement and routing. So if you see the converter which we will discuss from the starting, it has several parts which are given at ABCD. This input AC voltage terminal, B for EMI filter. So they are placed separately with some careful consideration so that one cannot interference any noise with into the other. So if you are using a power device, power circuit, and you put a signal circuit side by side, then it will put some error, it will put some noise, it will put some interference over there. And suppose if you have a, MOSFET and you put a uh, behind of it, suppose it's SMD MOSFET, behind of it you put a LDO for power supply. So that these are some uh, nonsensical error while designing the PCB. So you shouldn't follow this. You should avoid these errors. Okay. So next is placementing how the trace width. So obviously, whenever you are taking the traces for connection, it has some definite width based on the copper ounce. copper ounce, suppose 1 OZ, 2 OZ, based on which you have a definite trace width. There are some, I suppose, for if you're using KiCad or any other, or you have some online calculator for calculating the how much trace width we require for definite, suppose 5 ampere current, how much trace width we require. But a shortcut method to understand it, that suppose you are using a 1 mm width, it can withstand up to 4 times of bit current, suppose 4 amp. Okay. So if you're using a 2 mm width, you can withstand up to 8 amp of current. Okay. So this is a shortcut method to understand, but there are a lot of online trace width calculator. You can use that. Okay. So the clearances are very important in case of design. So otherwise that will create some problem. And next is ground references. Your power ground should have a definite other, analog ground, digital ground, chassis ground. All the ground should be separated and doesn't interfere with each other. In case of a power converter, if you're using a common ground, then doesn't have to look onto this, but you have to use a proper ground plane in your PCB, so that will matter the circuit. So otherwise, you see that the ground loop you should have to put in that way so that there is a the ground can come back. So these are called ground loop. Otherwise, there will provide some ground bounce, and you're supposed to get suppose zero at the ground, or you're getting some kind of millivolt or voltage, so that a ground bounce will be introduced into the circuit. So if you see this, that for designing a PCB, you have to use planes. So play the polygons in a sense. So that may be solid fill, that may be hatched copper tracks. They're like this. This is hatched polygon fill. This is solid polygon fill. Solid fill will have more copper, so it will help you to dissipate the power properly. And hatched has some vias into it, so it will also help. But this is basically a very old style using, and presently people use this kind of plain style. Okay. Next is routing style. If you see that this is a good routing style, uh, for the same thing, if you uh, so if you see that this is a good routing style, but this is a very bad routing style. So routing should be proper. It should be follows, doesn't be 90 degrees. So 90-degree following is very bad. You should have to follow that, it will follow some kind of 45-degree type of angle, so it will be better for routing. It will not introduce noises. If you see that this all the traces are in different lanes, so it will be not good in some cases for consideration. So the routing style is one of the major important thing. So this is all for the PCB design. While PCB design, you have to keep in your mind that first is a schematic, then you have to place the components, and then you have to route. For routing, you have to choose the trace width properly. The power require more, signal require lesser trace. Okay, and then the ground plane, the power plane. If you require some planes over there, you should have to put that plane, and you have to properly put the plane so that if you're putting two planes parallelly, they can introduce capacitance in between. So there are a lot of pros and cons. Someone say that you require to put planes, ground planes, power planes, you can put that. Some say that don't, you cannot put that. So this is very controversial, and you are able to learn it after your more and more PCB design experiences, that which is better and which you can use. So otherwise it will introduce some electromagnetic interference in your circuit. So noises can be introduced. So PCB design skill, you have to, you will get more and more skill after more and more design and understanding of it. Okay. So now we will solve some problem, the basic problems regarding this session. So some fundamental questions. Try to answer those questions, and I will give 2-3 minutes for each question. So this is, which of the following is not a type of a film capacitor? So try to answer it. And if you have any doubt regarding PCB design and how to design PCB, you can ask. Okay. So which of the following is not a type of film capacitor? Obviously single layer, no nothing like single layer. An aluminum capacitor is not into the film capacitor. Film capacitor can be of polypropylene type, PP thin film, or polystyrene type. Okay. Next, planes or polygons of different types of ground should be connected in dash node. An ESR of a capacitor is not affected by frequency, temperature, DVDT, DIDT. So try to answer it in the comment box also. Fine. So basically polygons are connected in star node like this. So the different types of ground should be connected in star node. And ESR is not depend upon the DVDT and DIDT rating of the component. Okay. Next, I have four questions. One is choose the acceptable reference interconnection, which would be a reference interconnection. Dash loop will introduce noise. Dash ground is connected to enclosure. Okay. Next is PCB layout, power electronic circuit, drivers and snowers need to be placed close to the power semiconductor device. True or false? Try to answer this. I'm giving 2 minutes. Okay, so I got some answer. So choose the acceptable reference interconnection. So obviously analog and digital ground. So these are some interconnection. Gate is not your reference. And the source of the MOSFET is not your reference. Negative rail is not your reference. Ground is obviously a reference. Okay. Net, that dash loop will introduce noise. Obviously ground loop, as I said, that ground loop will introduce ground bounce noises. Okay. And dash ground is connected to the enclosure. I discussed in the last class that a converter is put into the enclosure. Enclosure should have a separate ground, that is chassis ground, or you can say chassis. In the PCB layout of power electronic circuit, driver and snubber need to be placed close. Obviously, because snubber is used for reducing the noise that will introduce through your pulses, the PWM, the noise introduced into the PWM, and that will carry forward to your output. So obviously, the snubber should be placed closer to the gate driver. So that is true. Next, the last set of three questions, that reference of common mode in EMI is connected to dash ground. Have to answer the blank. And width of the traces doesn't depend upon what. Let's choose the correct option, number 9. So try to answer these three. This is the last set of questions. And if you have any doubt in between, you can ask about that also. Fine. So, reference of common mode EMI filter as discussed in the last lecture in detail, that is chassis ground. Choose the correct option. Buffer ensures maximum current. No. Sensing circuit and controller require interfacing circuit, obviously, for sending it into the microcontroller. Among all type of capacitor, ceramic can manufacture the highest capacitance. No. Refill current does not affect ESR. Definitely, refill current will affect because while designing converter, you see that there is definitely resistant capacitance, so it will produce some noises and it will introduce ripple. So width of the traces in PCB layout does not depend upon the cooling. That that doesn't affect with the cooling, how much a fan using, how much heatsink using. That doesn't have any effect with your layout. Okay, but it will depend upon the current, copper thickness, placement, obviously. So that's also that is the end of the course, and all the best for the exam. If you have any doubt, you can ask. And this is the last class, so we will meet somewhere someday in some different lectures in some different course, if possible. So if you have any doubt, you can ask. Otherwise, you can leave. So all the best for the lecture. Okay. So this is the course which where from you will be able to learn how to design power converter. So definitely try in future to design some power converter by your own. That will make some experience of your. So fine, that's it. So if you don't have any doubt, you can leave, and that's all for the day. Okay. Good night, everyone. That's